Hi students, this is Dr. Jo. Let's solve this problem. Okay, draw any chair conformation of trans 1,2-dimethyl cyclohexane. I'm going to pause there and draw a line bond structure to guide the rest of the problem. Okay, so cyclohexane, that's cyclohexane, 1,2-dimethyl, 1-methyl, 2-methyl, and then trans, I'm going to arbitrarily make this one a wedge and this one a dash. They are trans. Okay, then I can draw the ring flip. Oh, no, then I can draw the chair conformation. Okay, so I just do a line bond structure to guide my chair. So I'm going to start by drawing whatever chair is easiest for me to draw. Whatever orientation is easiest for me to draw with nothing on it. Okay, this is my carbon 1 and 2 here. I'm going to arbitrarily pick this to be carbon 1. And then this will have to be 2 to follow along clockwise with what I have on my line bond structure. Okay, on my line bond structure, I put the methyl up on carbon 1. That's going to be the axial position here. So this is up here. The CH3 would then be up, consistent, and that makes it axial on that carbon. Okay, then the hydrogen that's not shown on the line bond structure is going to be down equatorial. Moving down to carbon 2, it is down this position. That would be the axial position, axial down. And this is down. So in the line bond structure, the groups are shown as either up or down, but there's no axial or equatorial. Axial and equatorial only applies in the chair conformation. So there's a correct chair conformation of trans 1,2-dimethyl cyclohexane. Then draw the ring flip conformer. Okay, so I'm going to circle this carbon, follow it along. I'm going to first draw the ring flip without any substituents on it. Okay, now this is carbon 1 and this is carbon 2. So in my original chair, we'll call it A. Carbon 1 had a methyl that was up axial. When I ring flip, up stays up and axial becomes equatorial. So now this is up equatorial. Okay, and I can show the hydrogen there, and it is now down axial because it was down equatorial initially. Carbon 2, the hydrogen was up, so it's still up here, and that is now the axial position. Let me try and get that, there we go. And then the methyl is down still, and now it's equatorial. Okay, so that's a correctly drawn ring flip. Remember, I chose to call this carbon carbon 1, and so that set me up for this problem, but you could choose any carbon to be carbon 1. And then everything has to be consistent with that choice. Okay, analyze the two chairs and determine where the equilibrium of the ring flip lies. So we need to find 1,3-diaxial interactions, and we need to find gauche interactions. In chair A, I have axial substituents. So that means I have 1,3-diaxial interactions. Let's see, there we go. My pen stopped working. Okay, so let me get different color here to show those 1,3-diaxial interactions. So here's one axial substitution, it's on the bottom face. Arbitrarily number the carbon that it's on as carbon 1, and then 2, 3 carbons away, there's another axial group. There is a 1,3-diaxial interaction. It has nothing to do with the numbering system for the name. It's literally 1 and 3 carbons away, right? 3 carbons away. 2 axial groups. There's this steric interaction. So 1, 2, 3 carbons away, there's another axial group. There is a second 1,3-diaxial interaction. At the top, there is an axial group, carbon 1, 2, 3, right? There's always going to be an axial group 3 bonds away. So 1, 2, 3. There's another axial group, another 1,3-diaxial interaction. So as long as I have axial substituents, I have 1,3-diaxial interactions. And in this case, I have 4 1,3-diaxial interactions. between the CH3 groups and then the hydrogens that are axial. Each one of those costs 3.8 kilojoules per mole. Right? That's the strain added to that conformation by those 1,2 diaxial interactions, or 15.2. Now on the chair A, there are 0 gauche interactions. Okay, those 2 methyls are on adjacent carbons, but they're 180 degrees apart. So they're not interacting. There's no steric strain. They're not being brought together closer than the radius of the atom. So there are 0 gauche interactions. 15.2 kilojoules per mole is the strain added by those axial substituents. So then if we move over to B here, okay, there are no axial substituents, right? This one's equatorial as well. So there are no 1,3 diaxial interactions. But there is a gauche interaction, so 0, 1,3 diaxial. Okay. The gauche interaction is difficult to see on paper. It's easier to see on a model. We could also draw a Newman projection, and I will draw that up here. So I'm going to pretend to look along this bond to draw my Newman projection along the carbon 1, carbon 2 bond, and it looks something like this. So here's carbon 1, and this is the ring. And then there's an axial hydrogen pointed down. Okay, and then behind carbon 1 is carbon 2. So we can't see carbon 2, but we would see this hydrogen sticking up. Okay, then the methyl would be right here. There's our gauche interaction. And then on the other side, I'm just going to write ring for the rest of the carbons there. So there's that gauche interaction, but it's really hard to see it on paper. And if you can't draw the Newman projection, it doesn't really help you. So use a model, okay? Use a model. So there is 1 gauche. Also a tip, if you have substituents that are adjacent, so on carbons 1 and 2, and at least one substituent is equatorial, there is a gauche interaction. Okay, so 1 gauche between the CH3, that actually costs also 3.8 kilojoules per mole. The same as 1,3 diaxial interaction. So I've done this conformational analysis. I can look at the total strain added by the substituents in each ring flip and determine that the equilibrium of this ring flip should lie to the right, to the right. Remember, I chose what carbon 1 was on the original chair, and so that led to, the lowest energy chair being the second one, the ring flip. So the answer could have been A if I had started with the di-equatorial chair. Hopefully it makes sense that a di-equatorial chair is lower in energy, more stable than a diaxial chair, okay, which is A here on the left. Okay, if you found this video helpful, please give it a thumbs up.